Okay, the content of this lecture, today's lecture, is about hypothesis testing, and we are going to be testing the population proportion. That's our intention today. Okay, we have been already estimating population proportion by using Z confidence interval. This time we're going to be testing the claims about population proportion. And these tests are also going to be Z tests. So that means that we will need to have a backing of the central limit theorem. And in particular, we will need the fact B of the central limit theorem, which means that we will need to have a large sample. Okay, so how is this going to proceed? You could have some claim about the population proportion, like, I don't know, proportion of Americans that are smoking is 25%, all right? Something like that. That will be called null claim or a null hypothesis. You can correlate this, or you can associate this with the court trial. In the court trial, you have somebody who is accused, somebody who is presumed innocent and is brought to a trial as a charged person, charged with some crime. And then you have a prosecutor trying to convict that person, trying to reject his innocence. So he needs to prove that he's not innocent. And he's going to use some evidence for that, right? And at the end, there will be some decision made based on that evidence, based on how the trial proceed, to either convict him or to say that person is, we don't have enough evidence to convict that person, right? You are never going to end up trial saying this person is innocent. That is not what a court trial is about. It's about convicting the person or not convicting the person. So if the person is not convicted, doesn't mean it's innocent. This is always often said, and in our testing you will see also some people misunderstand that and end up testing and says, oh, okay, the beginning thing was true. No, we do not assume it is true if we do not reject. If we don't convict the person, we are not going to prove that that person is innocent. We are presuming his innocence right from the get-go. So you either convict the person or you're not going to convict the person, but you're not proving innocence. Innocence is presumed. The same thing here. So this initial claim is presumed to be true. Okay? You have to challenge that. So just like a prosecutor challenged the innocence of a person, you're going to challenge that with the alternative claim. And that alternative claim we will call alternative hypothesis. So you have a null hypothesis, null claim, often labeled as H0, hypothesis 0, null hypothesis. And then you have alternative hypothesis which challenge that. And that is going to be labeled either H1 or HA. HA is a hypothesis, alternative hypothesis, right? Okay, finally you need to have some evidence. That evidence is going to be a sample. You're going to have a sample that provides you with some evidence about what a population proportion might be. Obviously, the sample has sample proportion, not a population proportion, but it is some evidence about a population. So that's what we're going to have. We're going to calculate something that we're going to call test value, test statistic. So test statistics often called test value. Test value. That's alternative name for test statistics. I mean, it's equally good. You can use either. Sometimes we use test value, sometimes we use the test statistic. I'm ordinarily going to write T. And I don't mean T random variable. I mean just the test value, right? And it's going to have to be calculated out of the sample. So you have some sample, x1, x2, x3, some numbers, right, up to the nth one. So you're going to calculate test statistics out of that. Okay, so this is going to be your evidence. And finally, once you have an evidence, you will have to make a decision. That decision is going to be based on some criterion. We're going to call it rejection criterion. And that rejection criterion is going to be some rejection region. So if you meet some clause that is what we call a rejection region, if your test statistic falls somewhere when it shouldn't be, assuming that H0 is true, then you're going to say, well, okay, maybe this H0 is not true, right? So the test statistics should be behaving in a particular way if the H0 is true. Now, if that doesn't happen, then we're going to conclude that H0 is not true. Okay, so I'm talking generalities, but this is how it works, okay? By the way, again, so if the initial hypothesis is not rejected, then we're just simply going to say we don't have enough evidence to reject it. We're not going to say it's true. Okay, but here is how this works in particular. First of all, I already noted that all of the samples that we're going to use in testing proportion must be large, meaning at least 30 or more, because we're going to be using central limit theorem, fact B. And so here is an example. A claim has been made by the Political Action Committee that a certain candidate, political candidate in local elections, has a support of 55% of the people in the district. Okay, that's the initial claim. Proportion of the population supporting political candidates 55%. Always use decimal for any calculation, right? Not percentages. Then we have a sample. In the sample of 200 voters, we have 98 supporting him, and that would be less than 50%. It's actually 49%. So, all right, so now we, based on the sample, think that this initial claim is not true. Okay, we could use alternative, challenging claim, alternative hypothesis to be, well, it's not 55%, right? That's what we call two-tail alternative. We could also, you cannot do three things. You're not making three trials. You're making one test. So you can choose that P is less than 55%. Why? Because in my sample is 49%. So I think in the population proportion is less than 55%. They claim it's 55%, but I think it's less. So this is alternative claim, right? Challenging the initial claim. Or you can say it's more. That population proportion is more than 55%. Either one of these three would challenge the statement that P is 55%. Okay? This one is called right tail alternative. So the smaller numbers on the right side. This one is called left tail alternative, smaller numbers on the left side. We will see that in pictures very soon what it means. And this is called a two-tail alternative. Okay? So either left tail test or right tail test or two-tail test, depending what alternative hypothesis is. Left tail, right tail, or two-tail. Right tail, two-tail, left tail, right tail. This doesn't make sense in this case because our sample provides evidence that it might be different or that it might be less, but it doesn't provide any evidence it could be more, right? Our sample says it's 49% in our sample supports this political candidate. So it doesn't make any sense that we're going to be trying a test that is more than 55% because we don't have evidence for that, right? Like in the court trial, you're not going to try to convict Johnny B because you have an evidence against Eric S, right? So you, in this particular case, you can either select this as alternative hypothesis or this as alternative hypothesis. Certainly not this one, right? But in general case, if you don't have any evidence and you are just collecting evidence, you can start assuming either, right? So in our case, actually, we're going to use this. So this is going to be our alternative hypothesis. So alternative hypothesis is going to be left tail. So the whole test is going to become a left tail test. This is the setup of the test. Null hypothesis, alternative hypothesis. This is just a label, okay? H0 and H1 are just a label. It's a hypothesis, right? The colon stands for it. This is what it is, right? So this is the claim. Population proportion is 55%. That's initial claim, presumed to be true. This is the alternative claim, that population proportion is less than 55%. Also, keep in mind this number that is in the initial claim, we will call P0. So we're going to say, we're going to label this P0. Okay, that's presumed population proportion, because the claim says population proportion is equal to 55%. So P0 is 55%. That's what is claimed to be in initial hypothesis. That's why the P0, null hypothesis, P0, P null. Okay? So we are labeling this number, and we are assuming that this is indeed a population proportion. Okay? Now, we need to get some test statistic, and we need to get some rejection criterion. How are we going to decide? Okay, so first of all, let's think about what kind of mistake we can make. We can reject the null hypothesis is actually true. This is like in a court proceeding, you're convicting, rejecting the innocence. You're convicting a person that is actually innocent of the crime. So that's a serious error. Not only that you are making liability error because you're actively doing something and you're putting a person in prison who is innocent, but you're also making double error because you didn't find the actual culprit, the one that is really guilty. You are putting in the jail somebody who is innocent and keeping in freedom somebody who is guilty. So that's a problem, a serious problem. It's a liability error because you're convicting a person that is innocent. That's a liability. You're liable to that person. Or you can fail to reject the false claim. That's a type 2 error. If you fail to reject the false claim, if you fail to convict the guilty person, that is also an error. But it's a less of an error because you didn't compound that with anything. You did not put in a jail innocent person. So you would say, we don't have enough evidence to convict that guy. Or we don't have enough evidence to claim that the initial claim, null hypothesis, is false. So that's less of an error. Both are errors. So type 1 error is something we are mostly concerned about. Type 1 error is the situation when you're rejecting true initial hypothesis. Okay? That could happen. Just like in the court, you can convict the innocent person. We're going to try to minimize that. There is a probability that this could happen. The probability that this could happen, that you're going to make a type 1 error. We need to limit that. We're going to limit that with what we call level of significance. So level of significance is the maximum probability for us to make type 1 error. So maximum probability to make type 1 error is called the level of significance of the test. That will be something small. You don't want to have the probability of type 1 error to be large. So you're going to have maybe 10% if it's really not very important, or 5%, or 1% if it's very important. But in either case, this had to be something small, and you have to agree to that before you start tests. So you're not going to be adjusting your test at the end, what works for you. You're going to have to agree that before you start the test. You say 5%. Now we're going to do that in this test. We're going to say 5%. Okay, now how are we going to use this? And if you are assuming the level of significance of the test to be 5%, that means when you are rejecting a null hypothesis, if that is the end story, if you reject a null hypothesis, you're at least 95% sure that you're making correct decision. You're at least 95% sure that that claim was false, because there is only 5% or less probability that you made an error, right? So you have 95% or more confidence that that is false, that you're making correct decision rejecting it. Okay, so again, level of significance is that complementary to the confidence, right? Opposite to confidence, something small that you will set up as the maximum probability of making that type 1 error, rejecting a true claim, convicting an innocent person, right? Okay, so how are we going to use that? All right, first of all, let me remind you how do you do the sample proportion. Sample proportion, you pick up everything from the sample. It's either 1 or 0. You support this candidate, 1. You support this candidate, no, 0. You support this candidate, yes, 1. You support this candidate, no, 0, and stuff like that, right? Just sum it all up. You're summing it, basically you're just adding up the ones, and 0 when you add, you don't get anything. And then you divide, so you're adding up all of the things you have in a sample, and then you divide with n. So that's the average, right? That's the proportion in the sample. So in the sample, I have 49 of them, 98 of them support this political candidate, 102 do not. And so when I sum these ones and zero, I get 98. I have to divide it with 200, so I get 49%. So that's a sample proportion, okay? What do we know about this? Well, it varies from sample to sample. And one sample is one thing, another sample is another thing. So it's actually a random variable. Central limit theorem tells us, because this is a mean, central limit theorem tells us that this is a normal random variable in case you have sample mean. It's normal random variable in case you have a large sample. And we do. 200 is a large sample. Okay. What else central limit theorem says? It says that the sample proportion will have the mean to be a population proportion. Now we assume that to be P0, right? 55%. So we assume that's true. And then it also says the variance is going to be PQ divided with N. You remember that? If the variance is PQ divided with N, so we use that already in the estimation theory, in the confidence interval story. Then the standard deviation is radical out of that. And of course, since we assume that P is P0, 55%, then we can use that because we have actual number here. 55, this is 45. And this is, of course, 200 in our case. Right? What else we know? We know that if you subtract the mean of a random variable from a random variable and then you divide with standard deviation, you get a standard normal random variable. So this thing is Z. What else we know? We know about Z. We know that if Z is less than 1.645, that is unusual. It happens only 5% of the time. And you need to know this number actually, right? You remember this number. So we know that when you look at the Z distribution, so here is 0, and I don't know, 1.645 negative would be like here. So this is 95%. You remember the central area between negative 1.645, positive 1.645 is 90%. But then you have this tail here that is also 5%, so you get 95%, and this is only 5% here. Okay? That's what we know. This is very important for me to know. Okay? Why? Because that's my level of significance. So, this thing that I can calculate from the sample values, and I'll have all the numbers. This is 0, 55%. This is I'm getting from the sample 49%. This is 55%. This is 45%, right? PQ is the relation is 40-60, 30-70. It's complementary, right? And this is 200. So I have all of that. I can calculate this number. It should be going on here. 95% chance it's here. So if it happens to be here, we have a problem. That is unusual. That should not happen. So if this happen, if this calculation get me the number that is somewhere here below negative 1.645, I know the chance of that is only 5%. So that is something unusual, something that should not happen. Okay? It could happen, but it should not happen. Which means that something is wrong in our story. And what is wrong in our story? We use central limit theorem. That is not wrong. We use the numbers properly. We calculate it correctly. That is not wrong either. The only thing that could be wrong is that assumption in the beginning. We presume the initial hypothesis to be true. Well, that conclusion now should be that the initial hypothesis is false. So I did the calculation here. Lots of story here, but I did a calculation here, and I calculated P hat, the proportion of the sample is 49%. The P0 claimed and assumed population proportion is 0.55. That was claimed in the null hypothesis, right? P0 45%, Q0 55%. Remember, you always have to use decimal numbers, not percentages in your calculation. Okay, and 200. So you have to multiply these two numbers, divide with 200, take a radical. That's the denominator. Then you have to subtract 0.49 minus 0.55 is 0.06, and you divide that with whatever you have on the bottom. By the way, this is negative, right? When you subtract. And I ended up with calculation result to be negative 1.71. All right? This is by the way approximation, of course. But it happened to be below negative 1.645. So here's a picture. What happened? So my choice of level of significance of 5% gives me this tail. That's why the test is called left tail. It's a left tail. This is 95%. So the test value that I calculated, this is the test value. I have a formula for that. Should be z value. It's a z test. It's a z value. Negative 1.71. It happened to be here. Now that's a problem. But it should be here. 95% of the time it should be here. But it happened to be here. And again, that means that something is wrong. And that something that is wrong is our only assumption that we are not sure about it. That's the initial claim. Initial claim that population proportion is actually 55%. And we used it in our calculation. Right? P0. We use P0 instead of P in our calculation. So that is not right. Okay? That is not true. And I'm at least 95% sure that that is not true. There could be, coincidentally, the case that I just have, the z-value hoping that we have 55% of the population of voters in the district supporting this political candidate is false. And I'm at least 95% sure that it is false. Okay? Because the level of significance test is 5%. Okay? You always need to have this picture. Okay? If it's a left tail test, you'll be looking for a critical value on the left tail, so that the left tail is the value of your level of significance, 5% in this case, or something else. If it's a right tail, we'll be doing that on the right tail. So let me show you another example. Okay. If you want to test commercially manufactured dyes, what would you do? Well, this is important for the people that are producing that, right? They don't want to produce a fake or unfair dye. Some gambler might want that, but in general, most of the people don't want it, and certainly the gambling venues like casino and so on don't want to have anything like that. They want to have something that is fair. So it should turn out to be 6 1/6 of the time, 5 1/6 of the time, 4 1/6 of the time, 3 1/6 of the time, 2 1/6 of the time, and 1 1/6 of the time. Okay. So if you want to test one dye or you test the whole production facility, then you test multiple dyes. It's up to you. Like say here I'm testing one single dye. What would you do? I'm going to roll it 10,000 times and see how many sixes I got. That's a possibility to test like that. All right. So I'm rolling a single die. Maybe you want 10,000 dice and roll it once, or roll a single die 10,000 times. And I'm getting 6, 17, 21 times. Okay. Why am I talking about 6? Because on the side of 6, there is the most changes that you have on a die. So if something wrong in the production process, is going to be wrong on that side, right? Because you have the most changes. You have, indentation, possibly some coloring, and so on that side. So we are figuring out whether that side is more often or less often showing up. Okay. In general, you would assume a fair die. So that's our initial hypothesis. Null hypothesis: the die is fair. The proportion of the time that you would have the proportion of the time that you would have turning up 6 should be 1 out of 6 times. So that's, you can even write it down as a percentage. It would be 16.66666%. Okay, I'm going to keep it as a fraction. Proportion could be a fraction easily, like here. What we have here is that in this 10,000 rolls we get 1721 times 6. Okay, that's a 17%, 17.2%, which is more than 16.666%. Okay, so it seems to me that this 6 is more often showing up on the top. If I'm testing this die, now I have, this is a suspect. It seems to be more often 6 than it should be. It should be 1 out of 6, but it happened to be 1721 out of 10,000. Okay, so this is my alternative hypothesis. So this is my null hypothesis. My null hypothesis is that proportion of the times you're going to have 6 on the top is 1 out of 6. Alternative hypothesis is now that proportion of the time is bigger than 1 out of 6 because that is the bias I'm getting from my sample. Okay, again, you could assume two-tail. That is just simply not fair. It's not 1 out of 6. You could use that. You could use this one, right tail alternative. So two-tail alternative is in the game if you want. Right tail alternative you can use because your sample gives you educated bias. I'm thinking this is going to be more than 1 out of 6. 6 is going to show up more than 1 out of 6 times because that's what I'm getting in my sample. 1721 out of 10,000. You cannot use that is going to be less because you don't have no evidence for less. Right? Again, when you're convicting somebody or trying to convict somebody in the court, you're not going to be convicting another person because you have evidence for somebody else, right? Doesn't make any sense. So we're not going to use that. We're going to use right tail. So our alternative is going to be right tail. So this is a setup for the test. You have null hypothesis, you have right tail alternative hypothesis. Okay, this is our test statistic. So this is test statistic that we have learned that should be z-value, right? So all I have to do is to calculate that. On the top I have a p-hat, which is the what I got out of the sample. Proportion of the sample is 1721 out of 10,000. I wrote that like this. You can certainly write this decimal number, 0.1721, minus this guy. Again, you can write this decimal number, 0.166666666. Subtract. Downstairs we have a product of PQ, which P0, Q0, which is from the null hypothesis. 1 out of 6, the Q is 5 out of 6, right? Complementary. And then you have a sample size, which is, in our case, 10,000, very big sample. So we have a central limit theorem for sure. So that's downstairs. Now you have to be really careful. You have to multiply this two number correctly, divide with 10,000, take a radical. On the top you have to get this decimal, subtract, you're going to have some decimal, and you divide that, using a calculator of course, with what you have on the bottom, and this is what I got. Okay, I should have said that I want to use the confidence level and particular confidence level, significance level, and I'm using significance level of 10%. 10%. Okay, and this is a left tail test. So I'm looking for unusual thing to happen. I'm looking for the test value to be in the right tail. That will be unusual. It should be, again, around the middle. But to be in the right tail, that has a value of 10%, 0.1, right? 0.10. So that the whole thing here should be 90%. Okay, I need to know what that number is. All right, if this is 90%, this is one tail, 10%. So if you go for another tail, it will be 10%. The middle would be 80%. 10%, 80%, 10%. So I remember this number is 1.282 or 1.28. If you remember only two decimals, it's good enough. I'm gonna use 3. By the way, you can go and look at the t-table, down there. Uh, probability in one tail, what are we looking for? 10%. Down there, 1.282. So that's how you're going to be looking. You want one tail 10%, right here. Probability in one tail 10%, z value, this is all the rest of t values. Z value 1.282. Okay, perfect. So what happens with my test statistics? Well, it did happen to go above that, it's somewhere here, I think. Right? So it's in the tail. So our rejection criterion is, well, you have it in the tail or not? Is it gone somewhere when it shouldn't be? It should be somewhere in the middle where the most of the probability is. What happened to be here? Okay? So here's a picture, a little better picture than I made. So the test statistic happened to be above 1.282. It's in the tail. So this is the tail. This is called rejection region. This piece down there, the base of this tail, is rejection region. So it's in the rejection region, which means you should reject a null hypothesis. This is unusual. And again, the only thing that we assume that we are not sure about that is that the die is fair. This is our initial claim. We presume this to be true. And it turns out to be, because of this assumption, all of a sudden we get a z value that they happen to be when it shouldn't be very often. It could be. There's a 10% chance it's going to be in this region here, in this line segment, but the chance of that is only 10%. So that's a problem. And therefore, I am at least 90% sure that I'm not making a mistake, right? Because I love the level of significance to be 10%. The 10% is the maximum probability of making a mistake if I reject a null hypothesis that is true. But since that is only 10%, I'm at least 90% sure that the die is not fair, which means we have to go back to the drawing board to try to do something about it, because we're not going to be able to sell something like that, right? Or we're going to have a liability if we try to sell it. So again, the null hypothesis is false. So we are rejecting the null hypothesis. Again, we get the test value, 1.458. The critical value of the test, the critical value is the value we use for rejecting, where the beginning of the tail is, and this goes into the tail after that value, and that is the rejection criterion. So this is called a critical value. We call that the same thing. We call that the same thing in estimation. When we were doing confidence interval, we also call it critical value. It is a critical value in the test as well. Okay? One more thing to remember. When you look at this, what happens after the critical value, you have the area of 10%. When you look at the area, what happens after the test statistic, which is 1.458, you can look at the table. That happened to be what is called a p-value. P-value. And of course, if the test statistic happened to be in the tail, then the area starting with test statistic is going to be smaller than the area starting with the critical value. The area starting with the critical value is called level of significance. The area starting with the test statistic is called p-value of the test. So you can have another way of deciding when to reject a null hypothesis is when the p-value is less than level of significance. If that happens, then you know the test statistic happened to be after the critical value. It's in the tail, so it makes smaller area after that. So that's a rule of thumb. And now why am I saying this rule of thumb is important for you? It's important because the calculator will give you the p-value. So you won't have to do any pictures. If calculator will tell you, if calculator tells you 7.2% and your level of significance is 10%, oh, p-value is less than 7.2% is less than 10%, so I know that I should reject the null hypothesis. That's alternative way of making conclusion without pictures and tails. It means the same, but this is what the calculator does. For you, it would be a little bit difficult. You have to look at the table. I mean, how much is this area, right? The p-value. So it's easier to see, okay, I know this guy is after, so it's going to be in unusual positioning, somewhere in the tail. It should be around here, right? So I know that I should reject the null hypothesis. If I pass 1.282, I'm rejecting null hypothesis. If I don't, I don't. Okay. Okay, let's get one two-tail test, right? In a recent publication by Automotive Industry, it was claimed that only 16% of New Yorkers drive a pickup truck. Nationwide, that's known to be 21%, so this is not in a question. But the initial one is a claim. Only 16% of New Yorkers are driving pickup trucks. Okay, that's the null claim. Magazine claim. Okay, I went to Walmart Commons, 90 vehicles, and I counted 10 pickup trucks. So that's my sample. Maybe not a great sample. It's kind of convenient sample. I didn't do much randomization here. But I have 1 out of 9. Well, that's significantly less than 16%. It's like 11%. Okay. All right. So now I can say, well, the magazine is not right. I mean, their claim that it is 16% seems to be too much. I mean, I think it's less than that, right? Or I could just say it's different. So I can either use it's different, or I can use it's less. I cannot use it's more because I don't have no evidence it is more. So my sample is not telling me it is more. It's telling me it might be less. But I can also be unbiased, and I can say it's just not 16%. Okay. So this is my setup. Two-tail alternative. Okay, here is my test statistic again. So I have p hat, which is out of the sample, 10 out of 90. It's approximately 11%, but you have to calculate that. And then you have 16%, which is presumed to be true. Downstairs you have a 16%, 84%, so these are two complementary add up to 1. And then you divide it with 90, which is the size in my sample. 10 of them pickup trucks. Okay, after this is churned up, you got to use a calculator, calculate, multiply, divide, radical, divide, subtract, then finally divide this one with this one, and you get negative 1.265. Right, what level of significance gonna use? Customarily people use 5%. If you don't have any better idea, 5% is okay. Just like we were using 95% confidence level in confidence intervals. The level of significance is opposite to confidence. I should say complementary. So that's a customary 5% significance. For 5% significance, a true tail. So now both tail have to be 5%. That's 1.96, positive or negative. So what I'm going to say, now I'm looking for two tails because my test is two tails. I need to find the two tails that are combined 5%. And I do remember, so the central region is 95%. I do remember, I don't need to look at the tables, but if you look at the table, you're going to see the two tails 5%. Down there, Z value, 1.960. Okay, so if you cannot remember it, but I do remember, 95%, 96, positive 1.96, and now my test statistics. Is it in the tail? That will be here or here. Guess what? It is not. Right? So this was my rejection criterion. It was not met. It isn't smaller. This guy is not smaller than this guy. I mean, I know that. I mean, you need to know that, of course. The negative 1.265 is not smaller than negative 1.6, which means, now here's a picture, it isn't here. Conclusion, I don't have enough evidence to claim that the initial hypothesis is true. I'm not saying it is true. I'm just saying I don't have enough evidence to claim it is not true. Because according to my level of significance, is to reject the initial claim, I need to have a test statistic either here in this tail or here in this tail. That would be unusual. When it happens here, that is 95% of the chance. So it happened to be here. I cannot say it's unusual. Okay? And again, you can possibly get this calculator. I'm going to show you how to use it with a calculator. And you're going to have the same conclusion. So in the calculator, we'll be doing the statistical testing. We'll be testing for proportion, and of course we are using z-test. So this is one proportion z-test. No confusion here. Assumed 16%. The vehicles that pickup truck, the number of successes. This is the same old story we have a long time ago. Binomial roundabout. The number of success 10. The sample size 90. Proportion alternative hypothesis. So this is alternative hypothesis. Two tail, left tail, right tail. I'm selecting two tail because that's what my test was about. Calculate. There's some drawing here. Drawing is going to be much worse than this one I have here, so I'm not going to draw. I'm going to just calculate. All right. So it says your assumption was in alternative hypothesis is different than 16%. The calculation that we got, the calculator got is negative 1.26510. Okay, so it really fits my calculation, except that I have here much more precise and says this is a p. It's not a p that we are looking for. It's the p-value of the test. It should actually, the text instrument people should figure this out. P-value, to write p-value, not a p, because it confuses people. You're not looking for, the calculator is giving me p-value. P-value says 20.5%, so that's 20%, more than 20, 21% you could say. 21%, the nearest percent. 21%. P-value of the test, 21%. We use a level of significance of 5%. So the p-value is not less than level of significance, so no rejection. Okay? So that's that rule of thumb that I mentioned before. Your calculator doesn't care about your level of significance. You can use anything you want. But it tells you the p-value of the test is 21%. 21% is not less than 5%. The rule of thumb to reject a null hypothesis if you use a p-value will be that the p-value must be less than level of significance, and that is not the case. So that's the rule of thumb. P-value must be less than level of significance. It happened here, but not in this test. So this is a test that is inconclusive. We have concluded in this test that the initial claim of magazine that 16% of New Yorkers are driving pickup truck cannot be proven false at 5% level of significance. So we don't have enough statistical evidence to claim that that is false. Okay? Let's go one more. It has been claimed that the Super Bowl is watched by 1 out of 2 male Americans. So the 50% of male Americans are watching Super Bowl. That's a claim. Somebody made that claim. In a poll we conducted, it turned out to be that last Super Bowl was, the people that watched last Super Bowl was 128 out of 273 adult male respondents. So it's not all of that said, but of course we are, testing male respondents only, right? I guess it's only adult. I don't know. Maybe you can go for teenagers as well. Okay, so this is initial claim. 50% of male Americans are watching Super Bowl. 128 out of 273 is less than 50%. Okay, you can divide and you'll find out what that is. 128 divided with 273 is, I didn't press hard enough. 121. Okay, 273. 47%. Okay, 47%. Oh, it's less than 50%. I don't know. Now, this leads me to conclude I probably wouldn't get, the evidence is not strong. I probably wouldn't get conviction. So, the prosecutor in this kind of court trial will probably decide, I'm not going for it. But I'm gonna test it anyway because it doesn't cost me anything. I just have to calculate, right? It's not a cost like you have with the trial. So I'm going for less than 50%. So this is a left tail alternative. I'm using left tail alternative because in my sample I have 47%. I could also use two tail alternative that is not equal. So I could use here for null hypothesis, I could use not equal. I definitely cannot use bigger because that's not what I'm getting from a sample, right? So I have no evidence for that. Okay, test statistics. This is my test statistics, the same story as before. This is 128 or 273, whatever I get in the sample. This is presumed 50%. Down there I have PQ, each one of them is 50% because they're complementary, right? 40-60, 60-40, 30-70, whatever, 50-50. And the sample size is 273. When you turn this up in your calculator, it turns out to be negative 1.03. Negative 1.03. Okay. This is not really very important, right? Claim is not a big deal, so I can use the level of significance 10%. We usually don't use that high level of significance, so I'm allowing myself to make an error, a chance of error of type 1 error to be up to 10%. Okay, we usually don't go higher than that. Right, left tail. So I'm looking for a left tail that has 10%. So this is the 10% Z table. That is up to negative 1.282. Okay. This guy that I calculate turns out to be negative 1.03. It's here. It's low. This value. It didn't go into the left tail. It's here. It's not in the left tail, which means I cannot reject the null hypothesis. That's it. At a 10% significance, I cannot. You always have to state what is your level of significance, right? Because that's very important. If you say my level of significance is 5% and I'm rejecting null hypothesis, that means you're at least 95% sure that you're making correct decision. Okay? If you don't have a level of significance, you cannot have any confidence. You don't know whether you're sure or not sure about rejecting the test. Null hypothesis, right? About this stuff. So this is the last example. One more thing about this is that every single test that you make is about rejecting H0, null hypothesis. It's about rejecting. Okay, you're trying to convict this hypothesis. Okay? It's never about accepting it. Right? You have to be aware of that. So it's always about rejecting null hypothesis. If you do not reject the null hypothesis, the conclusion is that you don't have enough evidence to reject it. Not accepting it. If you need to accepting something, that is going to be H1, the alternative hypothesis. Okay? So if you need an acceptance of something, confirmation, something this is true, that's alternative hypothesis. So you have two hypotheses. The test is about rejection of a null hypothesis or not rejecting it, no enough statistical evidence to reject it. That is the same as accepting null hypothesis. When you say this is not true, then what is true? The alternative is true. Right? So if you need to accept something, that could be alternative hypothesis. So the test ends up with rejecting null hypothesis, which means acceptance of alternative. Or the test ends up no enough evidence to reject null hypothesis, which means no enough evidence to claim the opposite, to accept the alternative. So keep that in mind. Every single test is about rejection of a null hypothesis or not rejecting null hypothesis. Not about acceptance of a null hypothesis. The test could not end up with that. But if you need acceptance, you have another claim, alternative. So sometimes the test is set up. Somebody's going to ask you, is it uh, true that the number of male Americans watching Super Bowl is less than 50%. Oh, that is about the alternative. So you have to set up test that way. Okay, we need to test acceptance of something. We need to test whether it's true that it's less than 50%. Then the null hypothesis must be that it is 50% or more than 50%. Then the alternative is that it's less. Okay? So keep that in mind. The test, let me repeat this one more time. The test is always about rejection of a null hypothesis or not rejecting it. But it's never about accepting it. Okay? If you need to accept, that's going to be about an alternative hypothesis. Excuse me. Alternative hypothesis can be accepted. At the same time, you're rejecting null hypothesis. So rejection of a null hypothesis means acceptance of alternative. So the presumed innocence, the truth of a null hypothesis, if you're rejecting that, then you have a conviction, which means the alternative hypothesis charge is true. The person charged with crime, it's convicted. Okay? So again, keep that in mind, because it's never about acceptance of a null hypothesis. Right? Okay, this is the first part of the lecture, and the second part of this lecture, we will be talking about testing population mean. Right? So we'll do that later.